Oh yeah, superposition, that's where things get really strange.
Definitely. We're talking about, like particles existing in multiple states at the same time.
Whoa, wait, so like an electron spinning clockwise and counterclockwise at the same time?
Exactly. And it really makes you wonder, like, if this is happening all the time at the quantum level, why did it take us so long to figure it out?
That's a great question. And it kind of leads to another one, right? Like, why don't we see these crazy quantum effects in our everyday lives? I mean, why doesn't my coffee cup suddenly decide to be both full and empty?
Haha, yeah. Good question. That's where decoherence comes in. It's the process where a quantum system, like that electron or even like your coffee cup, loses its quantumness, and it all comes down to interactions with the environment.
So the environment is kind of messing things up.
In a way, yeah. Think of it like a perfectly still pond.
Okay, got it.
Now imagine dropping a pebble into it.
Ripples?
Exactly. The ripples disrupt the stillness. And that's kind of like how the environment interacts with the quantum system. Those interactions disrupt the quantumness.
So the environment is basically like the party pooper of the quantum world. Always like messing with those delicate superpositions.
Yeah, that's a good way to put it. And remember quantum entanglement? That spooky action at a distance?
Oh yeah, I love that one. But how does that fit in here?
Well, entanglement with the environment actually plays a big part in decoherence.
Whoa, really?
Yeah, the excerpt you shared about Schrödinger's cat is a perfect example. The whole cat in a box thing.
Oh yeah, the cat that's both alive and dead until we look at it. That one still blows my mind.
Right, so even inside the box, the cat is interacting with things like air molecules, photons, even the box itself.
I see, I see.
And all those tiny interactions cause the cat's quantum state, that both alive and dead superposition, to become entangled with the environment.
Okay, so the cat gets entangled with its surroundings, but how does that make it go from like a blurry quantum state to a definite, alive or dead cat?
Well, as the system keeps interacting and getting more entangled, those distinct states, like alive and dead, start to kind of like interfere with each other. But this interference is destructive. It actually leads to decoherence.
So over time, the superposition loses its coherence, and the cat becomes either alive or dead.
Exactly. It transitions from this uncertain quantum state to a more defined classical state. And this is why we usually don't see quantum effects in everyday objects. They're just too big, and they interact with their environment in way too many ways to keep those superpositions going.
That makes sense. It's like the quantumness gets lost in all the noise of the environment.
Right, and that brings us to something called the density matrix. It's mentioned in the source material.
The density matrix.
Yeah. It's basically a math tool that physicists use to describe the quantum state of a system. And during decoherence, this density matrix, it changes. It goes from a pure state, which is like a clean superposition, to a mixed state, which is more like a classical system.
So the density matrix shows how much quantumness is lost during decoherence.
You got it. It's like a snapshot of the system as it goes through decoherence. And what really stands out to me from these excerpts is this idea of decoherence being like a transition point. It's not just about things getting less quantum, it's about them becoming more classical.
So it's not just a loss, it's like a transformation. That's a cool way to look at it.
Definitely. And this transformation has some pretty wild implications.
I bet. I'm ready to hear more about those. Okay, so we've been talking about decoherence as like this transition, but how does it actually like play out in the real world? It can't be all just theoretical, right?
Oh, absolutely not. It pops up in the most unexpected places. Like, let's take quantum computing, for example. It has so much potential, right? I mean, imagine what we could do with it.
Yeah. I've heard quantum computers are going to be crazy powerful.
They really are. And it all comes down to those qubits they use. They're like the bits in our regular computers, but way more awesome.
How so?
Well, unlike our regular bits, qubits can be in a superposition of states. They can be both 0 and 1 at the same time.
Whoa. No wonder they're so powerful.
Exactly. But there's a catch, It's like building a house of cards in a hurricane.
Oh. Sounds tricky.
It is, because the slightest interaction with the environment can cause a qubit to lose its coherence, and that basically ruins the whole computation.
So decoherence is the hurricane in this scenario.
Pretty much. It's a huge challenge in quantum computing.
So how are scientists dealing with that? How are they, like, protecting those fragile qubits?
Well, they're coming up with some pretty clever ways to shield them from the environment. It's like an ongoing battle, trying to harness the power of superposition while keeping those qubits safe from decoherence.
It sounds super complicated, but hey, at least we're not dealing with cats in boxes anymore. So is quantum computing the only place where decoherence is, like, a big deal?
Not at all. There are so many other areas where it comes into play. Actually, sometimes we can even use it to our advantage.
Wait, really? Decoherence could be a good thing.
You bet. Think about quantum cryptography.
Quantum cryptography, that sounds intense.
It is. It's basically using quantum mechanics to create super secure communication.
And decoherence helps with that. How?
It acts like a built-in security system. Imagine you're trying to send a message and someone tries to eavesdrop.
Okay, I'm imagining. What happens?
Well, any attempt to peek at the message would trigger decoherence, like setting off an alarm.
So both sides would know that someone was trying to listen in. That's brilliant.
Right, it's like an unbreakable code thanks to decoherence.
Wow. So decoherence pops up in computing and cryptography. What other surprises does it have in store for us?
This might sound crazy, but there's actually growing evidence that decoherence plays a role in biology too.
Whoa, hold on. Are you saying that plants and animals are dealing with quantum mechanics?
It seems that way. Remember those excerpts you sent in?
Yeah.
Well, some of them talk about how scientists are looking into whether plants might use quantum coherence to, like, optimize energy transfer during photosynthesis.
So, like, plants are using quantum mechanics to become, like, super efficient at making energy.
It's a pretty mind-blowing idea, right?
Totally. And it means nature was hacked the quantum world way before we even knew it existed. Are there other examples in biology?
There's this really fascinating theory that birds might actually use quantum coherence to navigate during migration.
What? Seriously, how does that even work?
Some scientists believe that certain proteins in their eyes, these things called cryptochromes, could be sensitive to the Earth's magnetic field.
So, like, birds have tiny quantum compasses in their eyes.
Potentially. And it might involve quantum coherence, but of course decoherence is always lurking, making these things super hard to study.
Oh, right. Decoherence, always the party pooper. But still, this has blown my mind. Birds with quantum compasses. Nature is way cooler than I thought.
It really is.
But, all this talk about quantum stuff, it makes me think about that measurement problem again. Does decoherence actually solve it? Like, has it fully explained how we go from a blurry quantum world to a definite classical world?
That's a great question. And to be honest, decoherence doesn't completely solve the measurement problem.
Oh, so we're still a bit in the dark about how the universe decides what becomes real.
Pretty much. We know that decoherence helps explain how things transition from quantum to classical. But it doesn't tell us how the act of measurement forces a quantum system to choose one state. It's like decoherence sets the stage, but it doesn't direct the whole play.
So what are some of the ideas out there about how measurement actually works?
Well, some physicists think that decoherence is just the first step, They think it preps the system for some other process that ultimately causes the wave function to collapse during measurement. But then there are other interpretations of quantum mechanics, like the many worlds interpretation, that take a completely different approach.
Oh yeah, I've heard of that one. It's the one where every possible outcome of a measurement actually happens in a different universe, right?
Exactly. That's the one. It gets pretty wild.
It definitely does. Wow, this is a lot to take in. But it's so fascinating. Okay, before we get too lost in the multiverse, maybe we should take a step back and recap what we've learned about decoherence. Okay, so like we've talked about decoherence being this constant process, it's happening all around us, shaping reality. But if it's like always there, does that mean we never actually see any quantum effects in our daily lives? Is the quantum world like permanently hidden?
Well, that's a question that's been bugging physicists for forever. It's true that decoherence makes it really hard to see quantum effects in big objects, but, it's not totally impossible.
Really? So like how are scientists trying to peek into that quantum world with decoherence always messing things up?
One way is by, creating and controlling systems that show quantum behavior, but on a larger scale.
A larger scale. But aren't quantum effects all about those tiny particles?
Usually, yeah. But we're talking about systems that are bigger than a single atom, but still small enough to hold on to some quantum coherence. It's like finding that sweet spot between the microscopic and the macroscopic.
So it's like a balancing act, trying to make things bigger while still keeping those quantum properties. What kind of systems are we talking about here?
Well, scientists have been working with things like Bose-Einstein condensates.
Bose-Einstein condensates, those sound intense.
They are. It's where, millions of atoms act like one big quantum object. Pretty cool, right? And they've also seen quantum effects in things like superconducting circuits and even these tiny vibrating things called nanoresonators.
Nanoresonators, that sounds like something straight out of Star Trek.
Haha, yeah, kind of. But the cool thing is that these systems are letting scientists study quantum stuff in a way that's more, tangible. They're bridging the gap between the theory and what we can actually observe.
That's awesome. So does this mean that someday we could see, a baseball in a superposition state?
Haha, well, that's the million-dollar question. I mean, in theory, it's possible, but to do that, you'd need to isolate that baseball from its environment, completely. And that's insanely hard because there are just so many interactions happening all the time at that scale.
Okay, so no quantum baseballs anytime soon. Bummer. But still, it's pretty amazing to think about the possibilities. Thinking about all this stuff, it kind of makes me think about something that isn't really mentioned in the sources we're looking at.
Oh, what's that?
Well, we've been saying that decoherence explains how we get from the quantum world to the classical world.
Right.
But what if, decoherence is actually the thing that lets all the complex structures in the universe, exist?
Interesting. You're thinking like maybe without decoherence, there wouldn't be galaxies or stars or planets or even us.
Yeah, exactly. Like, imagine the early universe, right? It's just this crazy soup of quantum particles, all in superposition. Without something to bring some order to all that chaos, how could anything stable ever form?
You're saying that decoherence is what allows those quantum possibilities to like solidify into something real.
That's what I'm thinking.
That's a pretty cool idea. So decoherence, the thing that we've been calling the party pooper of the quantum world, might actually be what makes complexity and order possible. It's like it's shaping the universe as we know it.
Right. And maybe it even played a role in the emergence of life. It makes you wonder, you know, maybe that balance between quantum coherence and decoherence is what made it possible for all the intricate stuff that makes life work to actually evolve.
Wow, that's a really thought-provoking idea. It shows just how interconnected everything in the universe is. Studying quantum mechanics really makes you think about some pretty big questions.
It really does. Like, what is reality? How did all this complexity come to be? It's mind-blowing.
Exactly, and we've only just started to explore these ideas. There's still so much we don't know about quantum mechanics.
I know. This whole deep dive has been an incredible journey. From those mind-bending superpositions to the real-world stuff, and then, even thinking about the biggest questions of the universe.
It's amazing how it all connects.
It really is. And to everyone listening, if this has got you curious, keep exploring, keep asking those questions, and you never know what amazing things you might discover. So, yeah, keep that sense of wonder alive. See you next time.